Right.
Oh, hello.
You're like feeding your baby because I'm not happy. You're like feeding your whipped cream. What are you doing? What are you doing? Why are you feeding your whipped cream?
All right, guys, so just very quickly, make sure there's always two components to stats. There's the analysis, which is purely mathematical, and there's the interpretation. So I really want to make it clear, if we find a correlation between two things. So I feel pretty good to say that when I found the correlation between the number of homeworks that a student did and their grade, that correlation, I know it's there for a reason. But the funny thing is, I can't even say for sure that it's always going to be true because, for example, why might this be true? Salaries of teachers go up, and then we also notice that sales of liquor goes up at the same time. Why might that? Does that mean that teachers getting more money, we go out and buy booze?
It's a correlation, not a causation.
Yeah.
That just means they both happen to happen at the same time. If teacher salaries are going up, there's a very good chance that everybody's salaries are going up. And if everybody's salary is going up, the people that buy booze have more money to do so. Does that make sense? So it's either it's a coincidence. Very often you'll find a coincidence, a correlation coincidence. And there's a whole website devoted to really silly coincidence correlations. Right? So if you search for that, you'll find it. It's kind of interesting. Just these silly things. I used to have this thing I passed out where they found a correlation between the number of times somebody's hit by lightning and how many cats they own. That might be true. Maybe there is a correlation. Does that mean that having cats causes you to be struck by lightning? Some kind of static electricity kind of attraction? No, probably not. Right? But you can think what you want to, how you feel about cats. You can just ask one more evil thing about cats. It's they call lightning down upon their owners. Right?
You pet it, it creates
Exactly. So some kind of lightning rod effect. But I don't know if you guys are kind of with me. I can find correlations between, like there was a silly one, I can't remember if I've given you this example before, the height of a person and how much basketball they play or something, right? So that's, I can say, oh, you play more basketball, then you get taller. Well, that's just stupid, right? So just because there's a correlation does not mean for sure that one causes the other or the other way. There could be a third thing behind both of them, like the raising salaries of everybody causes everything to be bought more. Does that kind of make sense? So some things, though, correlation doesn't mean that something causes something, but it takes your attention and goes, oh, maybe there is something there. And then there are other methods to use to see if something causes something else. You guys semi with me?
Right, because in order to find causation, you have to find correlation first.
Well, no, not necessarily. I mean, there are tests for causality, sort of like the difference tests we did, the hypothesis test for differences. So I can see if a diet is effective by seeing what the weight was before and seeing what the weight was after, because that is a direct, and then that's the only change. If I can make sure that that's the only change is that they changed their diet based on this method, then I can say that was caused by that change in diet. Does that kind of make sense? So how many guys used to watch Mythbusters? Now it's going away. But very often they'll say we want to try to control for the variables. You want to make sure if you're making this change, you got to control for everything else to be the same, or else you're seeing a change in something else. You're measuring something else's change. Controlling the variables. Does that kind of make sense? Okay. All right, so I'm getting a little further away from it. My main message was, if you find correlation between two things, you can't say that this causes this or the other way around. You can't say. So correlation by itself is not good enough to say something like that. And so often correlation is misused in everyday life. You hear it on the news, well, there's a correlation between this and this, so therefore if you do this, then this is going to happen. Well, that's shit. Right? I can't listen to this person anymore because they don't understand statistics. Unfortunately, people in general don't understand stats, and they'll accept what they're saying. That's too bad. Not you guys. You guys know better. Okay. Just want to get that out there right now. Any questions from homework before we get to the last bit of new stuff? Any questions? So the thing we did last time was the chi-square stuff. Let me see, before I ask a question, does anybody need the handout from the chi-square stuff? I mean, I'm not sure how helpful this will be because this was done in class, but you can at least watch the video and go along with it. got that? Well, I also need the chi-square chart, right? Let's see if I have those. Between what?
Sour cream and motorcycle accident.
There you go. I like it. So is it a positive or negative? The more sour cream you eat, the more. Look at you. You found the website. Kick ass. 20 graphs of correlation. Completely unrelated.
You want to do that, man?
That's awesome.
I forgot I did the last one.
I love it. So they found a correlation between the amount of sour cream you eat, or the amount of sour cream sold probably, and the motorcycle accidents. Yeah.
There's another one for people who like strangle themselves with their own bed sheets, like on accident, like bed sheet accidental death, and ski resort profits.
Okay, good. I love it. Those obviously would be correlated, right? No, that's not an obvious. And sometimes it's a complete coincidence sometimes, right? Like, what's the probability that I get a head when I flip a coin? And what's the probability that I get an odd number when I roll a normal die? 50%. Oh, they're the same. They're cosmically really no. So sometimes, don't even talk. There's a whole website devoted to these, and I just wanted to tell you of its existence. I don't want to confuse you too much by showing you too many of the graphs, because it looks all very official, but again, you can show correlation between totally disparate things, just things that just happen to change the same amount at the same time. Sometimes it's like the income. Well, of course, everybody's income rose, so then more people can buy booze. And sometimes you can't find the link at all. You're like, why the hell would that be true? It just happens to be true. Doesn't mean a damn thing.
Well, maybe because they're affording more sour cream, so that means they can afford more motorcycles, and they're happier because they like sour
Sure, you can start to reach. Sure. Who else needs the chi-square chart? Nobody else need that chi-square chart?
Most of the time was correlation. Unless you got something accidents and...
Oh yeah, don't. Stats can get very morbid very quickly.
Like 3 other ones about suicide.
It's not a misleading title. Alright guys, so today, if there's no questions on section 11.6, so if you missed last time, we did section 11.6. Today we're going to do section 11.2. 11.1 is a introduction to chi-square, so definitions and kind of ideas, no big deal. That's going to be the last thing we do is section 11.2. Let me say this again. Make sure you guys are with me. I know. So 11.6, the reason I did 11.6 first is because it introduces the idea of the chi-square distribution in a format that we're already used to. So I like doing that. That's why sometimes I disagree with textbooks. Because that we already know about Haas's tests, even if however you feel about them. There's 5 steps. We know the steps. Good God, we've done enough of them. So now we just use a slightly different distribution and a different chart. Same steps though. 11.2 is awesome because it's a nice introduction to how to use chi-squared in different ways. 11.3 would be just a slight variation on that. So I don't mind, if we do 11.2, then those of you who are, anybody majoring in psychology, they have their own stats course that a lot of people take. Anybody majoring in education? One of you guys? Business sometimes use chi-squared. And the rest of you guys are just transferring, and you wanted to take 160.
Pretty much.
Okay, good. All right. So the rest of you guys, who knows? You might run into a situation. So what I want to focus on today is section 11.2. And let's do this first to make sure everybody's on the same page with me. And I'm going to do this focused a little bit on how it's going to work for today. Let's remember how to use this chi-square chart. So for example, say I had n equal to
I'll use yours.
15, alpha equal to 0.05, one tail. Let's say it's sigma, the claim is sigma, let's say H1 is sigma greater than 11. So where's the tail going to be? Where would the tail be?
Oh, to the right.
Yeah, exactly. So H1 always tells me where the tail's going to be. Right? Yeah, their normal distribution. Let's make a point of this. It's going to be over there. Now, when you do yours, if you draw a normal, just who cares? It's just an anchor, just a visual. I had people that for some reason they couldn't draw, so I just let them draw triangles for the normal distribution. What the hell? It's just an anchor for where things are. Hopefully, everybody could draw a curve. The triangle person, I just was like, just draw a triangle. Okay. So take a second and see if you can find out what the chi-square is for that. Don't say anything out loud yet. Just tell me, hold on, what's the area in there? Yeah, that's 0.05, right? And that's the way this works, is to the right. And the only reason I can imagine they did that is to screw us over. The other charts are all about to the left. This one's all about to the right. It's just the history of chi-square just came out that way. That's the way it's thought of. So let's see, what's the degrees of freedom going to be? 14. And I want 0.05. And the beautiful thing about the nice thing about this is the way this is set up is, if this is on this side of the chart is here, so I want to go over here. So 0.05 degrees of freedom is 14. So I want 23.685. Is that cool? Doing all right? Sweet. I mean, that's nice. So this chart, once you learn how to figure out z-score charts, t-score charts, this chart is very similar to the feel for how to find things. All right. I like it. So hypothesis test, if I'm doing a chi-squared, I'm using this chart instead of z or t. So it feels very similar. The thing about chi-squared that's different from z and t, what's the main difference between chi-squared versus z and t scores? Chi-squared can't be negative. So that's what leads to all these huge scores, because it starts at 0 and then it can go up from there. How we doing? All right. Okay. So something else that's going to help us out for today is, if a sample I picked had, let's say that the sample I get is 11, 11, 11, 11, 11, 11, 11, 11. That's my sample. What would the chi-square score be for that? How do you figure out what's the formula for chi-squared for hypothesis tests?
Wouldn't it be 0?
Yeah.
Because there's no standard deviation.
So if my data is 11, 11, 11, 11, 11, S is going to be 0. I love it. You guys, does that make sense? So a chi-square score of 0 would mean that my sample had no variation at all. I like it. So that's going to make today's topic make a lot more sense, because today we're going to say, what if I think that M&Ms in a bag should follow a certain distribution? Right? And then I actually get a bag of M&Ms and I write down what the distribution is. And I want to see how different they are. If they were exactly the same, then it should have 0. My chi-square should come out to be 0. Why? Because then the variation between the two would be 0. Does that by itself make some sense? I've got a handout about this too, so I haven't made it too concrete yet. Okay, the big thing to realize with chi-squared is I have a distribution that exists. I have a chi-square distribution that exists, but I can use several different formulas to calculate chi-squares to compare to that distribution. Right? So one we have is this. This exists in the world. This is this is actually the main chi-squared formula for chi-square distributions. But there's also another one that gets kind of interesting. Let's do a quick example of how to work this. Based on what I just said, let's say I expect a distribution to be uniform. Uniformly distributed. And if a distribution is uniformly distributed, what should that mean is true about every data point in there. So if there are, so for example, if my data points are all, let me say, like that. Yeah, doesn't matter. 0, 1, 2, 3, 4, 5. Right? If it's uniformly distributed, what would I expect to happen? If I had, let's say, if I had 60 observations I made, right? So I expect the distribution of TVs that people own to be uniformly distributed. So what that means is the number of people that have 0 TVs is the same as 1, is the same as 2. It's to be uniformly distributed. So how many TVs? How many people would I expect to have 0 TVs?
10.
Yeah, because there's 60 total people I'm talking to. I expect 10 here, 10 there, 10 there, 10 there, 10 there, 10 there. Let me stop there for a second. Why did I put 10 in everything? Because my expectation is that it's uniformly distributed. Why is that my expectation? Who knows? Right? It's just like somebody making a claim about something. Why is that their claim? Because they feel that way. Who knows? Right? You guys kind of with me? So this expectation could be anything. I could say I expect, 10% here, 20% there, 5% there. I can make a very specific expectation, or I can be very, vague and just say I think it's uniformly. Everybody has the same. So let's say that I talk to people and I actually get this. I actually get, let's say I have 7 people have no TV, 8 people have 1 TV, 9 people have 2 TVs, 11 people have 3, 4 people have 4, and then what do I have left? 24, 36, 40. 10 people have 5, it looks like, right? Is that right? Doesn't feel right. Feels like I left somebody out. 15, 24, 36, 40. Oh, 20. Double check on that.
I got 21.
Shoot. 5. No, it should be 20. It should be.
Wait, did I do 60 minus, 0?
Yeah.
These should all have to be 60, right? Because I'm talking to 60 people. Does that make sense?
Mm-hmm.
All right, I like it. So 15, 24, 36, 40,
Yeah,
60.
21.
Yeah.
What's 21?
All those add up to 59. So she's saying the last one should be
Oh.
21.
15, 24, 36, 40, 60. Don't they add up to be 60?
No, you're doing it wrong.
15, 24.
35. 35, not 35.
35.
59, 59.
Okay, so make that 20. Thank you. Yeah, I can't count very well. Addition is beyond me. Thank you for that. So then, these have to add to be 60, obviously, because I talked to 60 people. If I talked to 80 people, that would change this, wouldn't it? Right? This would get a little bit uglier because I want to distribute 80 people equally among 6 categories, but, then you bring in fractions or whatever. All right, how are we doing so far? So I really want this to make sense. So my expectation about how the numbers could be distributed, in this case, was easy. Uniformly distributed is beautiful, because then you just divide the total number by how many categories there are, right? I could have said, I think that the most is in the middle, there's 50% here, and then it drops off on either side, and then I'll have to take 50% of 60, 30% of 60, whatever, to figure out what these would be. So we'll do that kind of problem here in a second. So here's the idea. This kind of feels very familiar. How did we calculate standard deviation way long time ago? We took the data point minus the mean. And what's another name for the mean now? What do we call the mean also? Not the name for the symbol. And remember, what was that formula for xp of x? Sum of xp of x. And then the first few letters are exp, which reminds you that the mean's other name is the expected value. I love it. So aren't these expected values?
Oh, yes.
So I can do a lot like we used to. So these are expected. These are observed. So I can do my observed, my x, minus expected. X minus the mean. It's almost, you see, it's almost exactly like we did standard deviation a while back. So if I do observed minus expected, fill that in. What's observed minus expected for each one? What's this? Observed minus expected.
3.
Negative 3?
Oh. Negative 2. Negative 6. 11.
Let me stop there for a second. Is that cool? That's a lot like x minus mu. Now, if I add all those, does anybody know what's probably going to happen? It's going to have to be 0. There are going to be equal amounts above and below what I expected because they both add to 60. So what did we do before? Because they always added to be 0, who remembers? So what did we do? Squared them. Doesn't this feel very familiar? This is funny. It's all coming back to us. So I square these. So what do I got to get? 9, 4, 1, 1. I don't trust myself anymore today. 121. Now, of course, I left not enough room for the last step. The last step, let me see if I can get away from it. You guys just keep going if you have room, is observed minus expected squared divided by the expected, to do sort of a percent of what I expected kind of feel to it, right? So normally we would divide by the total number, and in fact I'm sort of doing that, dividing by the total number I expected in each category. So for the first guy here, so I'm going to put that here. You guys can handle it. There'll be 9 divided by 10, so 0.9. Each one is going to be divided by 10, right? So I could just put that right there. It's easy enough. So this would be 0.9, 0.4, 0.1, 0.1, 3.6, and 12.1. We stop there for a second. I just took each one divided by what was expected for each one. You stop there for a second. So it sort of feels a little bit like a standard deviation. It really isn't exactly that. And this is our first case where the first time we see that it really isn't exactly that. I'm dividing by what I expected to get a feel, sort of a squared percentage of what I expected, in a way. The difference between them. So if this was perfectly the way I expected it to be, what would all these be? 0, because the difference between them, if they were exactly what I expected, then the difference between them would be 0, which would mean I'm not at all away from where I expected it to be. So get this idea. Here we go. You ready for this idea? The whole idea here is to see the total difference, the sum of all the squared differences. How far away I was total. Is it big enough to show evidence that it actually is different? So 0 would mean it's exactly the same. That's beautiful. If I just get a little bit away from it, it's not far enough away from it to say it really is all that different. Right? I'm just taking a sample. So for the sample to show evidence, it's got to be really far away. Doesn't that feel familiar? That's the hypothesis test. You've got to be really far away. All right, how are we doing so far? So the one thing I haven't given you here is what alpha is to figure out what this critical chi-square score is. And how many tailed tests will this always be? Well, if 0 means that there's no difference, to show difference, it's got to be really far away from 0. And what's the only direction you can go to be really far away from 0? It's up that way. So it's a one-tail test up there. So if I get a chi-square score here up there, that's going to be evidence that it is different, that it wasn't uniformly distributed, it's distributed some other way. It's not uniform, right? But if I get a chi-square score in there, it's not enough evidence. It looks like there's not enough support to say it isn't uniformly distributed. All right, so this should all feel vaguely kind of familiar. So what is the formula here? The beautiful thing is, the formula, we basically have it. The formula for this chi-square, in this case, is going to be observed minus expected squared. Yeah, divided by expected. You add those up. So chi-squared here is going to be, if I add those up, what do I get? That last column.
17.2.
17.2. I'm going to take your word for it. So a couple things I got to fill in. So that, what do you guys think about that? I mean, you're not really sure what to think about that because these get pretty damn big pretty quickly, right? So we got to figure out which one of these scores is like my rejection region, right? Where does my rejection region, where does it start? So I got to figure that out. So let's use alpha equal to 0.05. How many categories are there?
6.
So the degrees of freedom is number of categories minus 1. That's kind of nice. Degrees of freedom is still n minus 1, but now n means number of categories. If I want to use alpha of 0.01, what chi-score would it be? degrees of freedom is 5.01. So what's the chi-square?
15.086.
15.086. Did we make it far enough away?
Yes.
What was our chi-square?
17.2.
So this is kind of like, I don't do this, but you guys can imagine. This is kind of like chi-square star, like my z star. If you want to do that, you can. You guys kind of, because this is the chi-square we calculated from our sample, isn't it? All right. So that's like chi-square star. And this is my rejection region. So did I make it into the rejection region?
Yes.
Yes, I did. I'm there. I'm 17.2. I like it. So did we show evidence that it isn't uniformly distributed? If it was perfectly uniformly distributed, where should my chi-square have been? At 0. If it was just a little bit off and not enough evidence, because there's only a sample, so hey, leave it alone. It could be anywhere in here, right? But we got so freaking far away that that's evidence that it is not uniformly distributed. So I'm not going to make you do all the steps for a hypothesis test, but that really is what this is. It's kind of a hypothesis test. But I want to get right to the point. Calculate chi-squared from the sample. Look up the chi-squared for your rejection region, and then you can just tell me, does it not look like it's distributed like that, or does can you not say it's not distributed like that? So here, it looks like it's not uniformly distributed.
So will there always be 6 categories?
No. Yeah, I could have had somebody say they had 6 TVs, right? Or the categories could be colors of M&Ms. On the thing I've got how many M&M colors there are. Or the category could be roll a 12-sided die, which is almost what I did today, and I thought, let's not do that.
Wait.
Hopefully we're okay with that.
So if you were to have 7 or something like that, or I mean if it would have gone up to 6, then what would be your extra?
Well, then the numbers would have been different. I would have talked to more people or something. It would have been distributed differently.
Okay.
Is that cool? Nobody said 6 TVs, so it just didn't come into play.
Never mind. Yeah, I was thinking something else, but yeah.
We thought it was like the column.
Yeah.
Not the like 0, 1, 2, 3, 4, 5. We're confused.
Like
Oh.
the expected, observed.
So this is the categories. Categories would be 0 TVs, 1 TV, 2 TVs. Categories could be, it's a little minor.
Not bad.
Categories could be brown, red, blue for colors of M&Ms. Categories could be, we're going to do something about cholesterol levels. So less than 130, between 130 and 200 cholesterol levels, right? It could be whatever the hell it is you're looking at. So what's really useful is, remember when they did the whole study and people got crazy about the Mediterranean diet because people in the Mediterranean seem to have better health and their blood levels are really great. Do you guys remember this at all? So there's an understood distribution of blood cholesterol levels. So if I find a little pocket of people that are somewhere and they eat a certain weird fruit or something, and I'm like, oh, is that the only difference? Then maybe that fruit, I should make it into little pills and sell it to people and make lots of money. So I'll do a study and I'll say, this is what I expect from what's known about everybody, how the cholesterol distribution is normally. And then I'll take an observation. I'll go take a sample of people and see what their cholesterol levels really are and do this test to see if there really is a difference. So let's do this. Let me give you guys, as I was standing up here, I realized one little thing I got to change on this, but it'll probably jump out at me pretty quick. By the way, this whole process, I love this process. It's called a goodness of fit test. So, math people know talkie well.
What do we call it? Goodness of fit.
So that's the official name. It's not something I made up.
You fit good.
It's called the Fit Good test. Yeah. Then it sounds like some high school presidential fitness award test.
You could have worked with
Fit Rich test.
How many people bought
That's so funny.
So, I gave you a fully worked out, well, I guess not fully worked out.
I thought she was going to show it to her mom.
What would the conclusion be up here I didn't quite give the conclusion for this. So you guys see, here's the, a little too bright. Holy crap, it's way up there. Alright, so my hand comes in. So here's another situation where we expect it to be uniformly. Try to see if it's not uniformly distributed. So if it was uniformly distributed, I saw 42 M&Ms in my little bag of M&Ms. So if it was uniformly distributed, they would all have 7. And then these are what I actually saw in the bag. You guys with me so far?
So this is like flipped, I guess? Because look at George, it's like expected, observed, and there's observed and expected.
Well, normally you put observed. It doesn't really matter as long as you do observed minus expected. And actually, the observed minus expected doesn't matter which way you subtract that, because you're going to square it anyway.
Yeah.
Right? So it really doesn't matter which way you order that. I just happen to say the expected first. So everything we did here is exactly what we did on the board. Oops. You guys are only looking at the board. It's too bad for you. Come to class. Alright. And then the last column is dividing the squared distances by each expected value. So then I got this chi-square value. This is I call it the critical chi-square value. So I had to get this far. So did I show evidence that it's not uniformly distributed? Where did I get to? I got to 3.143. So did I make it far enough away?
No.
No. So what could you say? We have
Failed to.
Good. So we have not found evidence to show that it's not uniformly distributed. You gotta love the double negative, right? You can't say that it is uniformly distributed because you can never prove the null. Okay. How do we feel about this so far? Semi-decent, hopefully. I really hope that this brings you back to the work we did when we calculated standard deviation. So here, I'm trying to see how far apart my expectation is from what I see. So it kind of makes sense to do the same type of thing. I want to see how far away those are, and that's exactly what standard deviation is. Okay, so let's try this one together. And anybody notice the kind of holdover? You can tell what Jeff did. He copied and then forgot to. You probably, hopefully, don't have a yellow blood cholesterol level. I'm not sure. Is that a threat level? Is that like the Homeland Security? We got cholesterol red, cholesterol not. Sure what it means. Okay, so here's our first. We've only done 2. So here's the third one we're going to do. But see, is it uniformly distributed? No. So we know, and this I tried to base semi-loosely on a couple websites that said they knew this. This is the distribution of blood cholesterol levels. And to be completely honest, it's not perfect because some of them talked about women only and some of them talked about everybody and so forth. But I just tried to come, I didn't really know what the numbers were, and it was hard to find something that just told me. So this is what I did. So let's pretend like this is true for some country somewhere. And then we find a group of 500 people that are living in this little secluded area, and they eat whatever diet they eat, and they do whatever they do, and we're like, well, let's see. Well, let's look at what their cholesterol level is like, because that's what you do when you first meet people, is you measure their cholesterol level. So how do I use this? So how many people were there?
500.
500 people. So if they matched this distribution, let's fill in the expected column here. And let's actually put the correct categories. Less than 130. Why say less than negative 130? Jump it down. 130 to 200. 200 to 240. And greater than 240. Right, those are the 4 categories. Is that cool? Obviously not the M&M colors to represent blood cholesterol levels. Although those seem to kind of go along together somehow. So what's my expected? How many people would I expect to have less than 130? How many people would I expect? How would I figure that out?
100.
500 times 0.20.
Yeah, exactly. This would be 500 times 0.2, right? I'd expect 500 times 0.2 people. 20% of any group of people is what I would expect to have less than 130. Does that make sense? If those numbers are true for everybody in this country, right, then I expect any group in the country to follow that. So I'm trying to see, is this group so far away from what I expect that there's something special about their levels? And hopefully they're low levels. If they're high levels, then I kind of say, let's not do what they're doing. So I expect how many? 500 times 0.2 is? That's crazy. So I expect 100 of these 500 people to be in this category, right? And I expect how many to be in the next category?
150.
150. Does everybody understand where those numbers are coming from?
Yes.
Let me know now if you're not sure. I'm just taking the percentage of the total observations I made. How many do I expect in this next category?
175.
175. And how many do I expect in the last category?
75.
75. And how do you check to make sure everything looks good so far?
You add them up, and that's
Yeah, so
500.
it's 300, 425, 500. Jeff can do math again.
Well, I don't know, Jeff, we'll find out.
Alright, so how many, so now you just fill in the observations. Obviously they have to give you either a list of observations and you collect them, or they got to give it to you like I do. So how many had less than 130? 120. How many had between 130 and 200? 240. Between 200 and 240 was 100. And the rest, what's the rest? I just got lazy there. 40.
460, yeah. 40.
Cool. So that makes a total of, bless you. So just to make sure that you caught everybody, just make sure that both your observed and your expected adds up to be the total number of people or things in your sample. Let me stop there for a second. How are we doing so far? Doing all right? Brilliant.
I don't know where you got the observed one.
Oh, I tell you right here, look, 120 have less than 130. So I put a 120 there. I tell you. So we see 500 people, and we take some blood from them while they're sleeping. 240 have between 130.
Okay.
Or we ask them, I don't know. I love the look on your face from this imaginary blood that I stole. That's awesome. Jeff, how dare your imaginary
That's like our extra credit project for like next semester. We have to steal blood from like 100 people.
Yeah, I like that. Jeff, we have something to ask you about. I don't know. My
you have tenure, man. So
yeah, text me a little bit. So what do I put here? I just kind of cut to the chase here. I don't want to make an extra column. So what's the difference?
20.
And then square it.
400.
400. And then the difference here is
90.
squared.
81. Well, 8,100.
Good. The difference here is 75, and you square that, you get what?
5,625.
All right, let me make sure right now, so everybody see where those numbers are coming from. It's okay if you don't, because if you don't, there's at least eight other people that don't. I'm going to take this to mean that you don't want to tell. Okay. And then the difference here is
negative 35.
35 squared.
1,225.
I like it. And then that's it. That's it. Blah, blah. And now we just take each one of these and divide it by what we expected. So 400 divided by 100 is 4. 8,100 divided by 150. Does everybody see what's going on now? Just divide each one by what was expected for that one. What's 8,100 divided by 150?
54.
54. 625 divided by 175.
32.143.
Cool. And then 1225 divided by 75. Bless you. 16.3. Alright, let me stop there again. So everybody see where that last group of numbers came from? That is useful. That's good. And now if I add those together, that will be my chi-square score. That's even better. Standardization on all those extra shit you had to do. What do I get here for my 106 sounds right. 106.4
4730.
up there.
Oh,
Yeah,
Something around there.
76.
that's weird.
Now, in general, just in case the book does this, because they do this sometimes, if they don't give you a level of significance, what do you think you assume?
0.05.
Yeah, because that's the most commonly used one. Because I don't think I gave you. Good. I think I messaged you that, but we'll see. So we'll assume that alpha is 0.05. What's the degrees of freedom? What am I trying to get now?
3. Your DF is 3.
Yeah, because there's 4 categories to 3. I'm trying to work towards what the critical chi-square is, what the rejection region chi-squared is, right? I know what my chi-squared star is, if you want to call it that. How many superscripts can I put on the damn thing? But hold on. So degrees of freedom 3. So if you look at the chart, 0.05, degrees of freedom is 3.
7.815.
Degrees alpha is 0.05. Degrees of freedom is 3, so it should be 7.815, right? If alpha was 0.01, I would look over there. So it's 7.815. That's how far away I had to get. Did we get that far away? Get out of there, normal. Jeez. You straw something so much. Like, oh my gosh. So we had to be, what did I just say? 7.378. Where did we get? What was our chi-square? What was ours?
106.
106. I kind of did that on purpose. Because I really, really, really wanted strong evidence. And then we would go see what they eat. So we fell out there. So what does that mean? That means that their cholesterol levels do not follow the pattern.
So Jeff, how'd you get 7.378? Isn't it 7.815?
Yeah.
I don't know where I got 7.378. Yeah, it's freaking me out. Oh, there it is. I see where I got it. Well, this is a good day for Jeff, I tell you. Good day for Jeff. Does that... So this is from there. So you can call it chi-square star if you want to, if you really feel like it. This one is the rejection region chi-square, right? Tells me how far away I had to get. We blew that bad boy away. Now, real quick, looking back at the data, that could mean either that they had better or worse cholesterol levels than expected, right? Right now, we just know that they're different. So how can I kind of get a feel for if it was better or worse? Well, I take my observations and I actually make them into percentages. So what percentage so for my observations, what percentage was in that first group? 120 out of 500, so that's 24%. How many in the next group? 240 out of 500. 48%. And the next group was 100 out of 500.
20%.
And then 40 out of 500.
8%.
8%. Is that better than what's normally, how it normally is? Why do you say yes?
Because the lower cholesterol.
Good. Lower cholesterol is better. And how many had below 200, which is actually the accepted kind of like marker? You want to be below 200.
Almost half. Or
more than half.
72.
Right? 72% had less than 200 cholesterol. So then we go, let's really investigate what's different. And then we got to try to do tests to see which thing is different. So maybe they run everywhere. Or maybe they eat a certain fruit. Or maybe they don't eat certain things. Or maybe they don't process any flour and sugar.
But
right?
hope to God it's not sour cream.
Oh yeah, because if they're riding motorcycles, they're in trouble, right? That's the thing. Like, wow. So it could be anything. Maybe it's they don't eat any brown M&Ms. I don't know. All right. But you see, I mean, this is actually, the funny thing about this test is it should, is new to you, but don't you get a feel for this math is not involved really at all? It's not very, it's not intensive math, is it? But it's a remarkably powerful test, really. You just have to come in with an expectation for some reason. So it's like you have to have a claim to get a hypothesis test started. So you have to have an expectation of what the distribution, what you think it should be. Is that? And then the test is not good enough. The test will just tell you it didn't look like it was that. So then you got to go back like we did and say, well, is it better or worse? If it's better, I want to do like they do. If it's worse, I want to not do what they do. Right? And then you try to make more detailed tests about, well, is it this fruit? So you can analyze it chemically. You can take test control groups and give some the fruit, some not the fruit. You know, you can start to really break it down into what's really different with how they live. Are you guys following me? So there's these two levels, at least, of statistics. There's exploratory statistics, very vague, very general. And then there's, well, did we see something interesting? Let's explore that in more detail. Let's make a test for this, make a test for that, make a test for this, and really see what it was that made this happen. And behind everything, there's a chance that we're wrong about whatever we find out. Right? That's awesome. Right? And don't say that's math's fault. It's not math's fault. It's just freaking life. We can't ever be 100% sure about shit. Right? As we know. Read the paper and they say, oh yeah, the thing we said 10 days ago, don't do that. It's bad for you, actually. Like, oh shit. Okay, let me see. Blah, blah, blah. Okay, so let me let you guys try one out of the book on your own. I'll put it up here on the overhead.
So do we have to write conclusions also for this?
Say again?
So do we have to write conclusions for this?
It doesn't have to be full blown. You can just say it's. And does this group match the general pattern? No. We've shown evidence that no, they don't.
Right.
That's all you need. Yeah, I'm not going to make this
About option.
really intense.
Then go to the
See if I can't find something. Well here.
دخل سمارت بقى.
I still have it.
الحمد لله. بعرف في البيت. يمجعيز لما.
Here we go.
It's about art
This is a nice
appreciation,
little
right?
simple one here.
Art
You have the book
appreciation.
with you. It's on
Your side of the
page
class.
609. Good. Do stuff. Do stuff. Alright, so there's. Oh my.
609. You said 609.
Make sure. Just to make sure you guys understand, this is sort of like the percentages on that last problem. So this is what we think it might look like. This is what the teacher thinks it'll look like, and this is what it actually looked like. So these lead to your expected values, and these are your observed values. So try to construct it. Use exactly the same kind of table setup I did, and do it. I'll start you off nice.